All right, so this lab is for linear momentum.
Recording in progress.
That's really simple. But no, you were doing 37. Yeah, because you went before me. Okay, but then earlier you couldn't. You couldn't come back.
So we're gonna use the online simulator again. So we can open another tab. So we're gonna use this URL to start our linear momentum lab. So basically what we do here, if we click to start, so click this one to start. So you begin. So what you do here is like this. This is astronaut Ali. It's his name Wally. So his name is Wally. So so he hold the extinguisher. So when the extinguisher start firing, so the propulsion force so the propulsion force will push the astronaut to move, and there are two photo gates. These two photo gates are 10 meters apart. So basically we're gonna study for the linear momentum around this process when the extinguisher start accelerating, and then he passed to this distance. This can be the time can be recorded here, and the momentum the astronaut gained, and we can also adjust the extinguisher's force and the Wally's mass and the speed we can monitor. So what we do here is we can go through step by step to see what we can understand. So so astronauts mass, this is here, we can adjust later the magnitude of propulsion force from fire extinguisher. So extinguisher force, that means the force when extinguisher got firing and then it start pushing the astronaut moving, right? And the duration of the propulsion force from a fire extinguisher. The duration of propulsion force from fire extinguisher, the altitude. So this time will be recorded as well. So when the extinguisher start accelerating, so the astronaut and the extinguisher will have the acceleration. So when they start, let's say it start acceleration into here, then the extinguisher is not firing anymore. So there will be, so because this is outer space, so the astronaut and the extinguisher will remain the constant speed to pass this photo gate. It totally depends on where we want it to stop. So we can try. Oh, I can show you one more time. I can show you one time. Let's see, activate. So you see, it start acceleration. You can shut off here. Let's see, I want to shut off here now. Okay, so basically when the astronaut reached to this position, the speed, so extinguisher is shut off. So that means from here to here, the astronaut passing with a constant speed and passes to photo gates. And the extinguisher, the time that extinguisher was varying for this for 7841 millisecond, and millis mass extinguisher's force. So basically, you can record this and put it in the table later, and then calculate everything we need. So all these three, so the time the extinguisher was varying, and the extinguisher's force and Wallace mass are three variables we need to control. So whenever we do any experiment, we only change one of the variables. So we can reset. Where the photo gate time is the time for Wally travel between these two vertical red lines, which symbolize the two photo gates. So basically, this is photo gate time. Measures the time when Wally passes to photo gate. And in this momentum experiment, why should you shut off the fire extinguisher before Wally reaches the first photo gate red line? So why we have to shut off the extinguisher before, let's see, before Wally passes the first photo gate, if we keep it accelerating, shut off. So if we don't shut off before the first photo gate, that means the astronaut always go accelerating. So you cannot measure. You don't have we don't have a let's see. So we want to keep this distance when Wally passes to photo gate line. So there's no acceleration anymore. So just like pass this two photo gates with a constant speed. Need to find another document.
You still there, Professor?
Yes, I'm here. Sorry, I'm here. I just want to find a document to make sure I deliver the right information. Okay. So we see the next one in this momentum. Okay. So which is Newton's three law of motion in effect here? So that means so let me see where they asked. Newton's three laws motions are in fact here. So we know when the astronaut is accelerating, that is when the Newton's. So can anyone can remind me what are Newton's three laws before I give the answers?
Newton's first law is an object won't change its direction of motion unless a force acts on it.
Yeah. Second.
Force equals mass times acceleration.
Correct. That's the third law.
I don't remember the third law.
Also, the third law is like you have a force work on another object. The object to give you back the same same magnitude of force and the opposite direction. So this is the I don't know the English word, but it's like you work on something. Like when I clap my hands. So when my right hand clap with the left hand also clap the right hand. So this is the third law. So just like you work on this one.
There's an equal and opposite reaction.
Sorry?
For every action, there's an equal and opposite reaction.
Yeah, right. So after review these three laws of Newton, so what we will see what we're gonna apply here. So when the extinguisher starts firing, the astronaut is accelerating. So that means which law is applied here?
Newton's second law.
Yeah, that's correct. So when there's a force, like basically the fire extinguisher's force gives the astronaut a force to do the acceleration. So Newton's second law applied here. And then also, so the fire extinguisher's force is basically for the fire extinguisher. But why it has an effect to the astronaut? Because they're like two things. They attach to each other. They do not attach to each other. It just astronaut hold the extinguisher. So in this part, so we applied Newton's third law because when the fire extinguisher start moving, sorry, I got confused. So basically, the fire extinguisher. So for a fire extinguisher, the Newton's third law applied here because this fire extinguisher. Let's see. So it just start pumping. Start pumping the air, right, to give the outer space a force. So the outer space will give the fire extinguisher opposite force. That's why the fire extinguisher get pushed away, and then it forced the astronaut to move with the extinguisher. So Newton's third law applied when the fire extinguisher moving. That means like when fire extinguisher pump the air in the outer space, the air in the outer space pump back. So that's third law. And then when we shut off the fire extinguisher, so the astronaut start moving. I mean, the will remain his own speed moving past to this photo gaze. In this stage, the Newton's first law applied. So basically, this is how they apply the Newton's three laws in the whole process. Okay, so next one, what is the fire extinguisher proportion effort doing to Wiley's body mass each second it is spraying? So like I said, when it's when the Ferrier extinguisher is spraying is spraying, then the altered space will give the opposite force to the Ferrier extinguisher and therefore to Wally's body or to Wally. And so what they ask is, so what is the Ferrier extinguisher proportion effort doing? So basically, Ferrier extinguisher's proportion effort, the force is, we can consider it's like an external force that work on Wally's body and give Wally acceleration to move. And how many different methods of calculation can you use to determine the speed of Wally? So how many different methods? So we have a lot. So because we have reset. So let's do one more time. So it start acceleration and it's counting the time. Let's see from we stop here. Okay, then pass. So so there. Okay, let me write down something. So when we want to determine the speed of Wally, so the first one is here when he passed this to photogate, because we shut off the Ferrier extinguisher before the first one. So from here to here, it's a constant moving. So we can do is so S equal to Vt, which is V equal to S over T. And we know as the photogate are 10 meters apart. So you know this one at 10 meters apart. And the time, they will record the time here. So here's, S1, let's see, S1, T1. So here is S1, T1. Because we have at least three methods to calculate the speed. So I don't want to get you confused. So that's why it's one way, right? And the second way is the momentum gain. So let's see. Let me just check the. So the momentum, we know P equal to mv, right? So V can be calculated by P over m. So this is the momentum gain. I would assume this is kilojoule. Yeah. So you can use this one, and the second one is we can use this one, acceleration speed. So we know this is the second one, momentum. And the third one is we use this one. So when the Ferrier extinguisher start accelerating, so the force we can do is to calculate. Okay, so the force, extinguisher force, equal to ma, and m is the Wally's mass, and equal to Wally's mass. And we can calculate A. So A equal to F over M. So once we get A, if we want to calculate the speed here, when the Ferrier extinguisher start fairing, so we can do V equal to V0 plus half AT squared, right? But since the beginning is a V0 is 0, so we can do V equal to 1 over 2 AT squared. So here is T. This is the T. So this is the T for acceleration time. So this is the external force. So does it make clear? Does it make sense?
Yeah, do you want us just to write down like these different ways, or do we actually have to do the math for this
You
question?
can just write down like the equations.
Okay, thank you.
You don't have to, unless they ask you to determine the speed of water. You can use one of the ways, but I want you to list all these 3 ways. You can calculate the speed. So let me see. I think you need to calculate the speed, but just use one way. You can stick to one method to calculate speed. When is Rayleigh speed changing during the spread of fire extinguisher? When is Rayleigh speed changing during the spread of fire extinguisher, or when the fire extinguisher is off? Obviously, it's when the fire extinguisher still spring, because that gives the astronaut acceleration. So which Newton's 3 law of motion apply at this moment? At this moment here. So when so that they ask you when Rayleigh speed is changing, which Newton's law is applied here. So obviously it's a Newton's second law, because when there's an external force for take effect on the object will have a acceleration speed. Okay, so you use your 3 variables: mass, volume, magnitude of proportion force. So this is F and E. Okay, I need to write it down. Text. Change to what color? So this is F and E T. What is mass? Is M volume. And the fire extinguisher time, this is delta T. Fire extinguisher time, acceleration time. Okay, this is all the information we need. So then say by holding 2 constants and vary only one at one time to create data set for 5 trials of each variable. So basically you do, okay, so 1, 2, 3, these are 3 variables. And then you change one of them and get to keep the other 2 constant, then you have a table, you create a table. Let me see how many tables you have. So you basically have 5 trials of each variable. So this leads to 3 data tables for 3 cases. So one is, let's say the first one, you can hold the force, which is extinguisher's force constant, and the Raleigh's mass constant, and you keep changing the duration of this time. So how you control this one? If I want to change the extinguisher's time, okay. What you're gonna do is, okay, so you can start accelerate. So you can stop here, shut off here. So you get the time here and reset. So I know my, and reset. So at this is so we shut off the extinguisher around this time, so we can start again. So maybe we start from here. We shut off here. So you basically have, okay, shut off. and we can shut off here. You just pick 5 different points to see, to control the extinguisher's fairing time. So this is for the first table. And for the second table, you keep the mass and the extinguisher's time constant. And you will vary the extinguisher's force and then fill out this table. Okay. So let's go over the first one before we jump to the second question. The second table, we will make sure you understand where to put all this data. Okay. So we'll go back to the first question again. So we keep the force and the mass constant, and we change the extinguisher's time. As I already showed you, when we can pick 5 different points, and we stop around that point, and we have a different extinguisher time. So at this time, if we keep Wally's mass is 7 kilogram, so it's all 70 kilogram, and F net is always 115. So always read the information from the screen and put it here. Delta T is if your extinguisher so let's say delta T is when you stop. So you basically read from here. So 5 times those will be different, and T gate. So you can record the time here. And the speed, remember we already go over all these 3 methods to calculate speed, but I think that I would probably use the most easy one by the V equal to S over T1. So this one you can use 10 meters divided by 800 milliseconds to get the speed here. And then they ask you to give another one, which is your force times delta T. So you basically the time times delta T. This is for the table 1. And so for the first one, for the first one you create a graph of F time delta T versus speed of Wally. So what does this mean? When we try to understand what the physical meaning, we should do math too. So we know F equal to ma, and V equal to AT, right? So when we do, so they ask you F time AT, time T, F time T, that means MA time T. That means, and we have to, because this gonna be y-axis, and this gonna be x-axis. So what we're gonna do is we have to convert the y. So the equation on the left have to be y, and the equation on the right had to be x. So which is the speed of Wally. So what we can do is, okay, so we can see the AT is V, right? So it's like F times T equal to M times V. So for the first question, we're gonna very likely get a linear graph that with the slope of m, because you see this is y, this is x, so the slope will be m. So this is for the first question. Okay, I'm gonna erase all of them because I think I record all this. If you have any questions or you wanna check the equations I read on the screen, you can go back to check the recordings. So right now I need some space, so I need to clean them out, but they all recorded on the screen. So, or you can take a picture, it doesn't matter. Let me see, eraser, erase all of them. let's see. So this is for the first table. So clear? Is it clear? So basically, this question, the first question is asked for the first table. The second question asks for the second table from the second table, and the third asks for the third. So basically, that's how it works. So this is for the first one, and for the second one, for the second question, so we're gonna hold M and T hold constant. And then we vary extinguisher's force. So basically, we're gonna make these two constant and change the extinguisher's force. So then you have a same mass for Wiley, and F net will be different at this time. And delta T, you try to keep it constant. I know it's very hard because you don't. So normally what I would do is when I find a reference when I want to shut off the extinguisher. Let's see here. Reset. So my reference is the first FortiGate. So I have to make sure every time when the extinguisher reaches to the first FortiGate, I shut it off. So this is my reference, even if maybe the fire extinguisher still varying for like a very little bit variance in the time, in terms of time, but it should be okay. You just like try to find a reference, because if we wanna refer to a star, it's very difficult. So I would like to refer to this one. I'll tell you what I mean by that. So I start activate. So I'll wait as the astronaut reach to this the first gate. Okay, so I record time 8973. Let's see. My computer is super slow. I hope I didn't make much error when I try to reset. So 8973. So we try to do another. We try to record the same amount of time to and shut off the fire extinguisher and activate. See, it's not identical, but still, it's very close. So it's like a millisecond. So you basically 8,000 milliseconds is a second, close to 8 or 9 seconds. So it should be okay. So don't worry about that if you cannot control the time delta T here. It should be okay. But just make sure every time for the second table, you're gonna vary the extinguisher's force. You can do a little bit. You can see, when I click the arrows, so it can go up and go down. So you can change that, and the fire extinguisher's time, you just try your best to record the same time to find a reference. And T gate, you still record the gate time here, and V, the speed. Remember, we have 3 ways to calculate speed, and then calculate the speed. And you don't have to do this one because F is not a constant anymore. So you don't have to do this column. But if you want to do, it doesn't matter. It doesn't. We are not going to use this column of data, because the second graph we're gonna plot F versus V. Yeah. So what we have is the second question. So what we're gonna plot is F versus V. So F equal to, still F equal to MA equal to M let me see, what's the slope of the second one? Speed valley. You have a constant, when we constantly changing f, so the speed of valley will be so maybe it's not a linear graph, you just plot because this is gonna be mv over t. So I guess your slope will be m over t and time v. So I guess this is your slope, but I'm not sure because right now I don't have data. I'm not sure what kind of plot it gives you. So you're gonna do this and figure out yourself. So this is for the second part, and the third part is when we keep the extinguisher's force and the delta T constant and the change Wallis mass. And then, so the Wallis mass, so basically Wallis mass will be different. The extinguisher's force will be constant. We try to make the extinguisher's time be constant. Even it's hard, but we try to make it close to each other to each time measurements. And the T gate, you can read it from here. And the speed, we can calculate it by 10 over T. And you don't do the last column as well. So we're gonna plot the third one, which is M versus V. So we know F equal to MA, and A has to do with the speed. And then when we see the F is constant, when we increase M, let's say we increase M, so F will be increasing. Wait. But we keep the F constant. So when we increase M, A has to be decreased. When A is decreasing, that means the speed is decreasing. Increase more little. It's not increasing that much. So when A is not non-zero, so the V always increasing because A is the acceleration. If A is not 0, so V is always increasing. Okay. If A is decreasing, but still as a positive value. Let's say A equal to 7 and 4 or 1, like that. It's decreasing, right? But then the V, cannot see. V will always increasing. Because if let's say V0 is 10, so this is 10, right? And if the acceleration speed is 7, so next second there will be 17. All right, you cannot see. Right? Just I don't want to confuse you when I say A is decreasing. That means V still be increasing. So then V1 will be 17, and V2 will be, because it's gonna be 4, right? It's gonna be 21. V3 is gonna be 1. It's 22. It's 3. That's 22. See, even it's just the magnitude of increasing becomes smaller, but still increasing. So that's what I mean. So you basically take you do the experiment and measure in 3 tables and create 3 graphs. Create 1 graph for each table. Okay, I want to write down somewhere here. Create 1 graph for each table. So okay, just make sure you can see that. Then you compare your graph to the momentum valley. So basically, how do you compare your graph to the momentum of valley? So basically, what we can see is from the equation, the first line. Remember the first equation we derived here? So the first one is F equal to M time, FT, right? The first question we ask FT, F time T, TA equal to MV. So this one, so that means the y-axis, this, do you feel like this looks familiar? Because this is the momentum, right? So the first one is actually the momentum versus speed. And the second one, how we're gonna do the second one? Second one is when we try to, so you see here MV, you just look for MV. MV is momentum. So this one equals to F, they ask you F versus speed, right? So it's F, so the second graph is F equal to P over T. Because MV is P. Oh, okay. We don't say any of these equations because it may confuse you. But it just tell me the momentum is. So when you change, let's say the first time we change the time of extinguisher. So we change this one. Basically, we change the acceleration time. So do you see the momentum is increasing each time? Or the second time we increase extinguisher's force, do you think the momentum gained at the limited amount of time, it's the momentum gain or decreased? It's just like you can tell me your discoveries after you finish all your measurements. So the third one is when you change Wallis speed, the mass, so you see the momentum is gained or whatever. Like you can find whatever you think is interesting. And then that'll be the end of this experiment. Any questions so far?
I have a question about the previous page. On the very last question on the first page, it asks again, which of 3 Newton's laws of motion are applicable? Sorry, I might have missed it if you said it, but is it like the same answer as the previous time they asked it? Is it all 3 laws?
So, okay, let me erase those things.
Sorry.
Oh, no. I'm so happy you asked because I know other students may have the same questions. So here so when Wallis speed is changing, so they ask you which 3 laws of motion are applied here. So when it's changing, that means the second law because the external force is affected on the extinguisher and the Wallis, right? And so this is the second Newton's second law. And here they ask you which Newton's three laws of motion are in fact here. So we have to figure out what's here. So in this moment experiment, it should shut off. So this is the first law. So when I explain all these three laws, where they apply here, I just want to help you to understand. You see here they ask you why we have to shut off the flare extinguisher, and which of Newton's three law of motion are in fact here. So that means like when you don't have any force, external force acting on the object will always keep constant or still, because the object here is astronaut. Astronaut has a speed, so it wouldn't just remain still. So it will keep constant speed moving. So that's the first law of Newton's law of motion applied here. I don't think they have anywhere asking you why we have to use the flare extinguisher to propulsion to, I remember somewhere. Extinguisher propulsion. Oh, they only ask you what is, you can say the Newton's third law applied here, because when the flare extinguisher propulsion, doing propulsion, when it's spring, then the outer space give the opposite force to the extinguisher and astronaut. So this is Newton's third law. But you don't have to say that, but as long as you can explain it well to make it clear, it should be fine, I think.
Okay, that makes sense. Thank you.
Thank you. Any other questions? If not, then that'll be all for today, and I'll take attendance. Let's see.
Hello, did you hear me say I'm here, or I don't think they.
I'm gonna. I haven't started yet, so.
All right, because I saw it and I was like, oh my gosh, there's zeros. Okay.
Oh, we're. I mean, earlier. Which one?
I think I'm fine. I got a little worried.
For the first column, let me figure out. Okay, so here. State. Is state here? See the alley? No. Angel?
Here.
Thanks. AL?
Yeah.
Wait,
Yes, here.
thanks. Malido? Let me see the chat. Oh, can you hear me? Can you guys hear me?
I can hear you.
Yeah.
I can hear you fine.
Yeah, we can hear you.
Thanks. Okay, so Malido is absent.
He's here. He was in the chat.
Oh, sorry. I'm sorry. We're Malido. Oh, okay. Okay. Yeah. Reid, haven't go to you. I know you are the last one. So don't worry. So Malido, I saw your message. Let me see. Alika.
I'm here.
Thank you. Ethan. Danny.
Here.
Thanks. Then Alexandra.
I'm here.
Thanks. Fahim?
Here.
Thanks. Fatima? Okay. Michael?
Here.
MD? Ronnie?
Here.
Radia?
Here.
Thanks. Jeff? Jeff? Brian? Brian? William? William? Khalil? Khalil?
I'm here.
Thanks. Tommy?
Here.
Thanks. Reno?
Here.
Thanks. Jamie?
Here.
Thanks. Adam?
Here.
Thanks. Gregory?
Here.
Thanks. You have?
Hi, I'm here.
Thanks. Varun?
Here.
Sarah? Sarah? Stephen?
Here.
Thanks. Yuan?
Here.
Okay, Raid, I saw your message. Let's see, copy. 24, do I miss someone? 24.
There was someone here before, but they left. As you
Oh
were
wait,
calling
wait.
names.
I don't think you got me. Brian Mackey.
Oh, Brian.
Yeah.
Okay. Okay, I guess that's all. Okay, thank you guys. If
Thank you.
you have any question, can write in email. I'll post the recordings as soon as possible.
Okay.
Thank you.
See you next week.
Bye.
Have a good day.
Bye.
See you.
Yeah, I got you, Reed. Okay, goodbye.